What is turn alternation and what does it tell us about how our brains work? Stay tuned. Welcome back, friends. If you're new here on this channel, we talk about all things psychology, so if that tickles your forebrain, consider subscribing. Today, we're talking about the psychology of spatial navigation, or how you get around your environment. But more than that, while this story tells us a lot about how brains work, it also tells us a lot about how psychologists work. That is, the kinds of pathways we take when we start to approach behavior scientifically. Your brain is an amazing organ, and it does lots of really cool things, but there's a cost. The brain makes up about 3 to 5% of your body weight, depending on, your quarantine Dorito consumption. But the brain consumes about 20% of your energy. That's huge. And nature doesn't like wasteful spending the way Congress does. So there are strong pressures to streamline cognitive processes to make them more efficient. Why use big brain when small brain work fine? This is sometimes what we call heuristics, which we've talked about before on the channel. Ways of creating simple rules that guide behavior that may not be right all the time, but get the job done often enough that they're worth following. In many cases, the trade-off between simplicity versus accuracy is worth it. Now, let's turn our attention to a difficult cognitive task that almost all animals have to deal with: navigation. If you don't think navigation is hard, you should try to program a robot to do it. It's a complex task with lots of variables. What kind of terrain are you in? Are there landmarks? Do things move? Does it change? Tides, snowfall, and winds can all dramatically change an environment in a short period of time. Well, let's take the simplest of navigational tasks, just moving around an object. A psychologist might ask, what's the absolute minimum cognitive machinery that you need in order to accomplish this task? Do you need to know the whole shape of the object and store that somehow in your brain? Do you need to remember where you've been already? So memory. How far back do you need to remember? Do you need the ability to plan ahead? Like, first I'm going to go left and then I'll go right. These are all different cognitive abilities that may or may not be necessary. So once we find a target behavior to explore, then we start breaking it down into its smallest elements to start testing them. Could you follow the rule, always turn left? Well, we know that can't be the case because that would just bring you around in circles. So we know we at least need to turn in both directions some of the time. Could it be a random left-right choice? What is the most efficient strategy? As it turns out, there's an incredibly efficient strategy for navigation that requires very little brain power called turn alternation. Basically, it does what it says. Alternating which direction you turn when you encounter an obstacle can get you around and through many obstacles. Now, to demonstrate this scientifically, we need to bring this into a laboratory. What we need is something called a T-maze, which is commonly used in all kinds of learning experiments. In this case, we're going to modify the T-maze so that it has a little alleyway leading into the T, which forces the animal to make a turn. When it gets to the T, it has to now make a choice, left or right. So the question is, will it choose randomly, or will it consistently go one way or another? Now, turn alternation suggests that if I force the animal to turn left in the first alley, it should turn right at the T. On the other hand, if I force a right turn, it should choose left. Now, what kind of animal should we choose? Aha! These little guys are known by many names: roly-polies, woodlice, pillbugs, sowbugs, cochineas, and oh, holy crap, look at the Wikipedia page. And that's just English-speaking countries? But a more scientific name for critters like this is isopods. Okay, before anybody complains about me using bugs on the channel again, let me just say, these little guys aren't insects. They're actually crustaceans, more closely related to crabs and lobsters than centipedes or beetles or other creepy crawlers. Side note, while they are related to lobsters and you can eat them, they don't taste very good. But that's a topic for another video. Maybe? Anyway, since we're interested in navigation, and these guys do have enough nervous tissue to somehow navigate their way into my bathroom from time to time, I think they're a great option for us to try and look for turn alternation. So I'm going to do a few trials here. I'll speed this up because we don't have all day, but I've got our official psi versus psi T maze ready. I'm going to block the maze so that they have to make a left turn before the T. I'll keep a tally of how many times they alternated, that is, turned in the opposite direction of the forced turn, and how many times they didn't. While she runs the maze a few times, let's talk about some of the things that could be going on here. If we see turn alternation, does that imply memory? And if so, what kind? After all, you've got to remember which way you turned last, don't you? Do you need to know the whole episodic memory, like what and when and where, and be able to picture the scene in your head like a movie? I mean, that sounds like it takes a lot of cognitive processing power. Or maybe you could just remember left or right. Or maybe it could take the form of what I would call a proprioceptive memory trace. A trace of memory about how you've moved your body and limbs in space. Or maybe you just have to feel that your left legs are more tired than your right legs. In other words, you wouldn't even need really the brain to store this information. But at that point, is it even really a memory? It's information being carried forward in time to guide behavior, which sounds like a pretty decent definition of memory to me, but it's not even being stored in the nervous tissues. So here we've got a dead simple behavior that we're studying, but it's raising questions about the very foundations of how we define memory. This is one reason why psychology has relied upon animal models, because it helps us trim away all the extra nonsense that we overlay on top of our interpretations of human behavior. For another example of this kind of phenomenon, see my video on social facilitation, which mentions social facilitation in cockroaches. Don't worry, there are no roaches in that video, I promise. Another good video to watch is our video on Morgan's canon, which talks about why we should start with the simplest explanation of a behavior. Now that video has psychic horses in it, so if you haven't seen it, you're missing out. Anyway, let's check in on her progress. Does she seem to be alternating? It sure looks like it to me. Now there are a ton of next steps we could take. What if we wanted to test some of those issues I was talking about, like fatigue versus memory? Maybe we could fatigue the left side more by forcing a bunch of right turns down a little ramp, and then force a left turn and see if the fatigue disrupted alternation. Or maybe we put little weights on her legs. Or we could ask how long the turn memory lasts by testing longer and longer runways until they stop alternating and the choice becomes random. Now, in the literature on this, they've explored turn alternation in many species, with dozens of papers just using isopods like we're doing. They've shown all kinds of things, such as how giving multiple forced turns in the same direction can make the turn angle at the choice point bigger. They've also shown that putting a little treadmill on one side so the legs have to work harder makes them tend to turn in the other direction. Now, these results suggest that turn alternation, in isopods at least, involves differences between left and right leg movements, which they call bilaterally asymmetrical leg movements, or BALMs. Other research shows that the coloration of the maze floor can disrupt turn alternation. Also, the presence of predatory spiders makes the tendency for turn alternation stronger. One interpretation being that turn alternation helps ensure navigation away from danger. Now, turn alternation has been observed in many species, but one particularly interesting case is in humans. Well, not exactly. Human sperm. Okay, I know that's weird, but think about it. Sperm have a strong need to outcompete the other sperm as efficiently as possible, navigating a gauntlet that puts Ninja Warrior to shame. So maybe it's no surprise that they use turn alternation to get from point A to point egg as effectively as possible without a brain. Heck, they don't even have neurons. They're a single cell. They don't even have a full set of genes on board. So that's an introduction to the idea of turn alternation, an incredibly efficient way of navigating through your environment with very little brain power required. It raises interesting questions about what we consider memory and why, and goes to show that sometimes real science can be done with brains you find right in your backyard. Now, as a note, no animals were harmed during the making of this video. Remember to return your new friends to where you found them and leave them some vegetables as a reward. If you liked this video, say thanks with a like. If you want to see another video about some of the cool and surprising things that isopods can do, or if you want the full story of how I know what isopods taste like, according to science, leave a comment below. Consider subscribing because we've got a lot more content on the way about all things psychology. And until next time, keep thinking. I know I said brains don't like wasteful spending, but somehow I've still got that Juicy Fruit jingle from like 30 years ago still bouncing around my head, and it makes an appearance from time to time. Juicy fruit is gonna move ya. It's got the taste. Apparently evolution thinks I need to know that.